There we go. Okay. Hey, everybody. I'm Joe. You may know me from the internet as Joe Wilm, and I'm here tonight to talk about Alacritty, a GPU-accelerated terminal emulator. The project's on my GitHub, jwilm/Alacritty. If you haven't already checked it out, I highly encourage you to go grab the source and build it. It's super easy, and I think you'll really like it. So here is a screenshot of Alacritty. I'll give you a demo at the end, but I wanted to include this screenshot because it really shows that this is a working terminal. So we've got Vim running inside tmux, running inside Alacritty, and it just works. I've been using it as my daily driver for the last several months, and it's fast, and at least for what I'm using it for, it's correct. So why would anyone say my my terminal emulator isn't fast enough? We need to put this on the GPU. If you've used like iTerm and tmux and Vim on macOS, you might have encountered that it's sometimes slow. And I got frustrated with this enough that I started thinking about doing something with it. And then Patrick Walton last year gave a talk about web render. And I'm like, this is exactly the thing that terminals need. And one of his arguments for this was about processor chips. So maybe for you, your terminal is fast enough, but it's hard to argue that if you're only using one CPU core, that with today's hardware, you're wasting your computer's potential. If you can move more of these computations onto the GPU, you obviously have more room on the CPU for doing other work at the same time. So this is the Intel Kaby Lake die. It's a whole half of the chip is GPU now. In Patrick Walton's original presentation about web render, he kind of shows a progression with the GPU taking more and more space. And this is kind of where we're at today with the most modern chips from Intel. If you look at CPU usage of iTerm versus Alacritty, or a lot of other terminals versus Alacritty, not to pick on iTerm, but you can see this is running find/, so just find on your whole directory tree. On a 2013 MacBook Pro, iTerm's taking 4 times as much CPU as Alacritty. Obviously, this is kind of a contrived benchmark, but you can imagine if you're doing real work that your terminal emulator is staying out of your way and your CPU is free to do the work that you really care about. Why Rust? There's two CPU cores here. We should be able to use both of them really easily. CPU cores are probably going to continue to increase, and we should be using them, and we shouldn't be fighting with bugs related to concurrency when there's a language like Rust that makes it so easy to avoid them. The type system. Encoding constraints of the program into the type system is hugely valuable for developer productivity. If you can describe your problem in a way that the compiler can statically prevent you from making dumb programming mistakes, that's a huge win in my book. And then speed. Alacritty is all about speed, so systems language is obviously necessary for the best performance. So for most of this talk, I wanted to tell you about actually building a terminal emulator in Rust. And I've got this architecture diagram, which is kind of a high-level representation of what Alacritty looks like on the inside. So there's 2 main threads here. There's the display thread, which kind of does all the rendering. It also processes like keyboard events and mouse input. And then there's the I/O thread, which talks to like your shell, parses the output, and then updates this terminal structure, which you see in the middle. The terminal structure is kind of sitting here overlapping the two because it's shared state between these 2 threads. So basically, your pseudo terminal gives you data, the parser parses the data, the terminal stores that data, and then the renderer over on the display side is going to actually show it to you. So we're going to start by talking about the pseudo terminal. This is the first thing you need to get your terminal up and running. So when you launch a program, whether it's Alacritty or iTerm or anything else, you just have that one process. You don't have a shell or anything to talk to yet. It's just you alone in this cold, dark world of the computer. So the first thing you do is you call openpty. And what this does is creates this pseudo-terminal pair. It's really a couple of data structures in the kernel. They're like super special cased, but we can just think of it as a bidirectional pipe. So after we set this up, we've got a file descriptor for each of these, the master and the slave. We can call fork. We get another process. We connect that process's standard input and output to the slave end of this and spawn our shell. Now the shell starts talking and bytes go out to the slave and they become available on the master, and now Alacritty can start looking at that data and doing something with it. So this whole process is just to get the shell available, or whatever program you want to run inside the terminal, up and running and providing you data. So after we have the data, we want to parse it. So this is a really simple state diagram, right? So there's this guy, don't try and understand this, by the way. So there's this guy, Paul Williams, who has spent just like a ton of time looking at DEC's original terminals, like physical terminals, and kind of mapping out the observed behavior of, if you press a key, what happens? And he's done just an excellent job of it. This is, all of his research is online. And so other programs use this, like Tmux implements this directly. And so we do the same thing for Alacritty. So don't look at too much of the detail here, but from a high level, we just translate this diagram. So the outer block is a procedural macro. So it's basically a compiler plugin. Not stable today, but there's a way to just kind of have it output the product of this to a file, and you can track that in your source tree so you can still compile the result on stable. But basically what this is we've got on the left, there's this list of states, and then those map these ranges of bytes to another state in an action. So we go from our current state, we get some input, and then we get another state out of it and maybe have an action to run as a result. The procedural macro outputs something that looks like this, but then it all gets wrapped up in this nice little function where you provide your current state, a byte, and you get your next state and potentially an action out of it. So that brings us up to the VTE parser in this diagram. So we have our stream of U8s from the pseudo terminal. We parse those, and then we get these actions. Those actions get delegated to this VTE perform type, which is a trait. It turns out these actions are still really low level. We want to be able to think in terms of like go to this line or go to this column, scroll down, that sort of thing. And so this trait implementation actually maps that to another trait, which defines all these high level methods. And then finally we update some state on the terminal itself. And so like we have this really nice abstraction here where we just go from byte goes through the parser. We get these low-level thing. We map that to a high-level function like going to a line. But that kind of sucks for performance. But thankfully, these two generic types can get completely inlined at compile time. And so it looks like the result is actually the byte comes into the parser, and then state just gets updated on the terminal. So instead of going through all these layers of abstraction, when it says print a character, it'll actually just update that character immediately. So that brings us right up to what does the terminal data structure actually look like. This is the last thing we need before we can go display it. So basically, there's a grid of cells and a cursor. These are like at least the things relevant for displaying it. There's kind of a bunch of other properties on here. The point type is what the cursor is represented by. It's a line and a column. So this line and column are new types on usize, and this is really helpful. I'm about to show you why. But you can imagine that a point is going to fully specify a location in the grid. So the grid is just a two-dimensional vector, essentially. So we have a vector of rows. If you index it with a point, you can get this reference to whatever this container is holding. If you index it with a line, you can get a row of those things. If you index this with a column, that's not implemented. You'll get a compiler error. If you index it with a line, though, you get a row back. And now you can index that with a column, and you can get at your t. So we can index a grid with a cursor. We can index it with a line and column. But if you try and transpose that, you're going to run into an error. Now, this high-level trait type I was talking about has these methods like goTo, which take a line and a column, or scroll, and it'll say 10 lines. These are all strongly typed. So if we try to, in one of these methods, index the grid incorrectly, like trying to transpose which cell we're interested in, the compiler will actually stop us from doing that just because we took the time to define these new types and use them everywhere. So this is really powerful. I'm terrible at this. The reason I actually added it is because I kept running into these bugs where I would, mentally swap the argument order and everything would look horrible. Cool. So we've got our terminal, basically a grid of cells, and we want to display that. And the renderer is really why Alacritty is fast. To understand why Alacritty's renderer is so much faster than iTerm, we have to talk about rendering styles. So traditionally, if you're using a 2D graphics API, you might say draw a rectangle here, and the API will dutifully go and say, okay, yeah, you said it should be this color, so I'm going to put this rectangle here. And then it comes back after you waited for it. Then you're like, okay, put this character here. It should be this color, this location, and the API goes and does that. It updates its data structures, and you wait for it. And so if you do this for 40,000 characters, which would be a very large terminal window, that would take a lot of time. The alternative rendering style is retain mode. So instead of iterating through your grid yourself and calling all of these methods that take effect immediately, that draw rectangles and characters immediately, you're going to take your state and describe it in a way that the GPU knows how to consume. And then the GPU will be able to optimize how that's drawn. So naturally, Alacritty is going to fall into this retain mode category. And by doing so, the whole terminal, everything you see, can be drawn in only 2 draw calls. So that's one call for the background of the cell and one call for all of the characters themselves. So the other part of this story is that rasterizing a glyph, so you need the letter A. You call out to free type and you're like, give me the letter A, it should be this big, this many point sizes, at this DPI, and it'll give you a buffer back. And if you did this for every character every time you needed it, you'd be waiting forever. And so all of the glyphs that get rasterized are uploaded into a texture atlas. So now when you go to make these draw calls, all of the data is already on the GPU. This is what I was saying with retain mode. We're putting all of our data on the GPU in a way that it's easy for it to consume. So with that in place, we can make use of instance drawing. And now what that means is we're going to describe our per instance data. So you can imagine that a cell in the terminal, you've got the letter A, and it's got a background which might be gray, and the foreground is white. That has some per instance data like the line and the column. The line and the column and the texture data, the foreground color, the background color. So we put this together in a big, huge list, upload that to the GPU, and now all of those items can be drawn in parallel. This is an absolutely huge win for performance. And then it also has the nice effect of minimizing data sent to the GPU. So instead of sending a whole bunch of redundant vertex data or uploading textures over and over or switching textures constantly, all of the data is kind of described in a very concise format. So to give you an idea of what instance rendering does for us, how we really implement this in practice, I want to talk about just mapping a line and column, which we think about in this grid, to something the GPU can take and actually display to us. So if you think about like the background for a character cell, it's a rectangle. A GPU primitive for display is a triangle. So we need 2 of these triangles. Each triangle has 3 vertices, and so in total we have 6 vertices. This is a quad. But our display list only needs to specify the line and column. So that's, if you consider that each vertex has at least an X and a Y position, that's 12 data points in total, and we're just going to upload 2 data points in total for each of these items. The other piece to this puzzle is that our shader uniforms, we tell the GPU, hey, the cells are going to be 10 pixels wide by 20 pixels tall, and now the GPU can figure out exactly where to place that cell, all 6 of those vertices. So I've got an example here. So say we are looking at cell in line 2, column 10. So this is our instance data. Now, we tell the GPU that each cell is going to be 10 by 10 pixels just because that's easy math. And then we also have to give it a set of vertices to work with that will work for every quad that we ever want to draw. And so we give it essentially a unit rectangle, which is 0 at the origin, and then the maximum size is 1, 1. So the first thing we do is we add our line and column offset. So now this is a cell that's been translated over to this line and column. This is still just like a logical idea in our application. We multiply this by the pixel data, and all of a sudden we've got all of our vertex data fully specified, and we've only uploaded 1/6 of the data that the GPU actually needs. So in this way, we can do this with other stuff too. So like the texture data just gets mapped right out of, we just tell, we in our instance data specify the location in this texture map, and then the fragment shader will actually go look that up at draw time, and we don't have to be constantly uploading textures or switching textures or uploading this buffer. So performance-wise, this gives us really good results. So on a full screen of text on a 2013 MacBook Pro, integrated graphics, so semi-old hardware at this point, we get 2 milliseconds per frame. If you look at VSync on a 60 hertz display, that gives you about 16.7 milliseconds per total between frames. So that leaves a total of about 15 milliseconds where the display is not, or the renderer is not doing anything, and the parser can run. This is the main reason that Alacritty is absolutely fast. The parser gets all this uninterrupted time to run. We don't have to try and optimize for when we draw. We know that if we've drawn in the last 15 milliseconds that we aren't going to need to draw for a while, and we just wait for basically for the buffer swap to return, and then we know that we can draw again. And so this has the effect that text that comes and goes between these frames never has to be rendered. So testing Alacritty, we obviously want this thing to stay correct. So we have this idea of ref tests. This is something web browsers have done for a while. Basically, a web browser would take some HTML, some CSS, and some JavaScript and run that through the layout engine and then compare it against a known good result. And so if it's very different, you know that there's something wrong. If it's identical, you're right where you want to be. Your test passed. So Alacritty does the same thing. Our data looks a little different, though. We have a recording of the terminal protocol and then a serialized grid of the terminal cells. So basically, we just create our terminal, run all this protocol through the parser, and then compare the grid state at the end. The grid state has things like the characters, any modifications on the cell, like underline and italics, and the colors. So we know that if this grid state matches, that it's exactly the right result. Generating ref tests is incredibly easy, too. Basically, you pass this ref test macro with Alacritty, and it'll output a new recording and the serialized terminal state for you at the end. And then we've got this macro where after you do that, you just add the name of this thing. And now for each of the identifiers in this macro, you get a fully expanded test, an independent test from the others. So you know precisely which one has issues, if any. And this would actually be a great use case for procedural macro. Right now, all of these tests live under this test/ref directory. It would be really easy for a procedural macro to list through all those files and then expand test code for each of them versus us having to manually manage that ourselves. So yeah, roadmap for Alacritty. Right now, we don't have great Unicode support. We support UTF-8, but like, you know, we all really need emoji in our terminals. So we need fallback fonts because your favorite programming font almost certainly doesn't have emoji. This is also really important for international users, of course. Xterm compatibility. This is really important, as it turns out. So Xterm is like this really old terminal that has just been battle tested. It supports more features than any terminal really should. But every command line program in existence basically works correctly in Xterm. And so claiming Xterm compatibility and actually meeting that is a huge win for us. We've got this Mesa bug. Mesa is this open source OpenGL driver implementation, and it seems to affect a number of Linux systems that use this. If anyone knows about Mesa, has experience with this, I would love to talk to you. It seems to have about slows down Alacritty by a factor of 10, so that's like really bad. More benchmarking. We've been able to get away without a whole lot of rigorous benchmarks so far because the initial experience a lot of folks have had has been very positive. It has been the fastest, but moving forward, we need more benchmarks. We want to be able to maintain our claims about being the fastest, so more benchmarks. So a lot of people haven't installed this yet because building from source is kind of a pain if you don't have a Rust compiler. So we want to start providing binaries so anyone can get going with this quickly. And then after all this stuff is kind of in better shape, we're going to be looking at an alpha release. And then as far as performance work, display list generation is currently on one thread. So you can imagine that if we could just fully parallelize that, that would be a huge win. The parser can't run during those 2 milliseconds when this is happening. So if we can even just cut that in half, that would be a huge win. Glyph rasterization jobs are currently done on in the same process as this display list generation. That could easily be parallelized as well. Another huge win. And then accessing the pseudo terminal. So while we're doing this render, the terminal is locked. The terminal state is locked, excuse me, and the parser can't run. This also has the effect that the program that is running in the shell is not running if it's producing a lot of output because the buffer gets full. So parallelizing access to the pseudo terminal with the parsing and with the rendering would also be a huge win. Yeah, so if anyone wants to get involved, the best way to get involved is to try this thing. Download it, build it, run it, use it. It's very usable. Like I said, I program in this thing every day. Tell us about your experience with it too. So come on the issue tracker, come on IRC, Alacritty on Freenode. And then if you want to contribute to it, I'm more than happy to do mentoring on issues and help you get started. We've already had several people contribute to the project who had never programmed in Rust before, so that was super cool to see. So I wanted to give you a quick demo, and then can take some questions. So, all right, I am skeptical that this is going to work particularly well on AV equipment, but it turns out, according to this Hacker News thread, that the first thing anyone wants to do with a new terminal is cat dev urandom. That actually works pretty well. So Alacritty no longer has issues crashing on this. And I'm actually really impressed with the AV equipment here. This is really smooth. This is cool. So, okay, so that works. We might want to do something else like, let's look at all the code. Oh, that's not how you list a bunch of files. Yeah, so that works pretty fast too. It's not quite as smooth on these displays, but that's okay. If we want to open an editor, we'll find that Vim works quite well. Scrolling is quite smooth. Yeah, that's about it. I would love to take any questions you guys have.
So how did, usually when you cat dev urandom, there is a bunch of junk in there, including what the terminal will interpret as control codes, which then leaves your terminal in some weird state, and you have to STTY sane. How did that not happen with Alacritty?
I don't know. The prompt comes back every time.
That's so weird.
I agree.
So how tightly coupled is the rendering engine to the rest of the terminal? Meaning that, like, if one day the implementers of iTerm come to you and they're like, this is awesome, we want to use it, how difficult do you think that would be?
I have a slide for that. So, okay, this is how you tell the renderer to render things. If you can give me something that is an iterator for indexed cells, so an indexed cell is just a cell with a character and a color and a background color and any attributes like underline or italic or bold. And then the indexed part is just a wrapper that adds the line and column. So this is just plain old data. If you can give me an iterator that looks like that, I can render your thing.
So yeah, first I wanted to say that's super impressive. Like the scrolling was so smooth. That's awesome.
Thank you.
So I think a lot of people have had a dream of integrating graphics into terminals. Like this goes back to the 80s with like Dex Regis and stuff like that. Not that I suggest you implement that. But like, especially with web renders back end, like I think there's a lot of potential for what you could do with that, provided it maps onto this sort of like cell model. So I know like iTerm has a sort of like proprietary-ish extension for rendering images in the terminal. Have you thought about adding anything like that, or?
So first part is I didn't mean to give the impression that this is backed by WebRender. It was just totally inspired by WebRender.
Okay.
So
Yeah,
like a lot of the graphic strategies are basically taken right out of WebRender's playbook. As far as actually implementing stuff like being able to display images, there's a project called Naughty by someone who's here named Without Boats, who has been working on essentially protocol extensions for the ANSI protocol to be able to support like saying print, show me this, like catting a ping, essentially catting like a JPEG and showing it to you. So yeah, it's I haven't had time to follow up with him as much as I would have liked, but it's definitely something we're looking at. So right now we're at a place where we're a really fast terminal emulator, but terminal emulators haven't advanced for a while. So we are kind of looking at it as an opportunity to try and push the state of the art.
So you said that the rendering takes about 2 milliseconds, during which the parser can do nothing, but the whole terminal data is like a very small amount of memory. Can't you just clone it and then display that and continue parsing?
So yeah, I've thought about doing a copy on write strategy like that, and honestly, I just have not tried it. It's a really good idea. I don't know how. So the thing that you'd have to watch out for is like a large screen is going to end up being about 40,000 cells is the number I've been using. That's like 400 columns wide by 100 lines tall. And So if you have like 16 bytes of cell data, it's not that huge, I guess. Was that 40,000? You're not even at a megabyte, I think.
Right.
So it might be that you could just, copy this every time, or like do a double buffering sort of strategy.
Have you written sweet shaders to make it look like an old CRT yet?
No, I have not, but there is a project for that. The CRT space is very crowded right now. CRT emulation space.
Just one more question. Have you thought about making some of these bits network transparent? One of the things is if you're running something that's producing a lot of output on a server, and you have to like backhaul that across, say, a slow link, that can actually be a big bottleneck. But if you're running the parser on the far end and you're just transmitting across frame data, that could be potentially a lot faster. Could this be like possible with the code base?
So that would be a much deeper integration because now the shell on the remote machine would need to be aware of the terminal emulator running on the other end.
Which you definitely have to be running part of Alacritty on the server.
Yeah, it's an interesting thought. I don't know that it would. It seems like it might be a win in terms of bandwidth, especially if you're able to, if it's faster to just send, every time the frame needs to be refreshed, send the whole grid state versus, you're catting gigabytes of log files. That might be a big win. I hadn't really thought about that before, though.
That's sort of the strategy Mosh uses, except that it doesn't, like it then renders to a traditional terminal emulator again. So you kind of have this back and forth running the state over and over again.
So I think this is a great project, and I'm really excited. And I run Windows, and I'm wondering when I can use it. So the real question is like, what's like the technical things that need to happen? Like what is missing or what is different?
So first of all, I know nothing about Windows. I've got gluten, which gets me really far as being able to run the renderer on Windows. Windows doesn't have a PTY subsystem like Linux does, but it's from what I understand, the Linux on Windows subsystem provides some sort of way to hook into that so that you can use most of the same. I really have not researched this enough, but I've looked enough to know that it's possible, basically. The main things stopping it at this point are just that no one has done the work and that we're on a gluten fork right now.
Have you tried messing around with hooking this up into the Vulkan and seeing if there's...
So I really want to add a Vulkan render, actually.
Me too.
OpenGL was a really good first choice because it works on literally every system. But Apple, the wonderful company that they are, has not added support on Mac OS yet. So yes, I would really love to have a Vulkan render. It was just that OpenGL allowed it to run anywhere from day one.
Could you use a shader to directly map the row and column and character and attributes into pixel data or into texture coordinates without having to do that on the CPU side?
So we do a lot of this on the GPU already. Maybe I'm not understanding the question. So the instance data that we upload is the line and column, and then we've got a glyph cache which records for every character with every font face specifically where in this atlas that glyph is located. So that's a top left and a bottom right. So now we've got that's two more tuples, and then this is about as minimal as it gets. The GPU then using the data like the known cell dimensions is able to calculate right where the whole outline of that box is, and then using some of this other glyph data knows that the glyph is going to be inset this far, and it knows right where to look that up in the texture atlas. Does that sort of answer your question? I don't.
Yeah, I think that's pretty much it.
Okay.
Have you looked at any of the things that use shaders to generate characters from outline data?
So, from what I've been told, the glyph cache is going to probably be more efficient than trying to calculate this for every frame on the GPU. It is a really interesting idea to basically describe all this data on the GPU and have it like calculate all that on the fly, but from the people I've talked to, it sounds like it's not generally a win in terms of performance, just because the glyph cache has such a high hit rate.
Yeah, it's probably true for a terminal thing where all the characters are the same size and stuff. If you're dealing with lots of different scalings or something like that, then
right.
Maybe it's different.
Yeah, that might be a win for like web browsers.
So as a very small addendum, because I don't actually know much about this, that there's the Xi editor that Rafe, whose last name I can't remember, is working on in Rust, has like implemented supposedly the fastest font renderer in Rust. That is, I have no idea how it's doing glyph rendering. It's supposed to be amazing. Okay, well, yeah, but
it's not. He talked about it.
He's not here, so I didn't want to
He's not
speak
here,
for him.
but Patrick is actually working on like basically web render, but for glyphs. So doing glyph rasterization on the GPU, and right now his benchmarks are giving really good results. But I don't think he's mentioned it a couple of times in public, but I don't think he's actually released. Like, I don't think he's released 1.0 yet.
It's really exciting.
Yeah.
Yeah, so everyone forget that we said that because so he can have a nice big surprise. Any other questions? Okay. All right. Well,
Thanks, everybody.
yeah. Thank you, Joe. All right, and that concludes another wonderful evening. Thank you, everyone, for coming. If any of you have any ideas, any Rust talks that you want to give, please come up and talk to me, or find me on Meetup or IRC or the internet. Yeah, so thank you for coming. We have the space available for, I don't know, probably another maybe 30 minutes, hour or so. So hang around. Thank you. And see you next time. Yay. I love you all. Except for that McFerrin guy. He's the worst.